Welcome, and it's time for another optimization problem. All right, so a rectangular field is bound by a fence on 3 sides and a straight stream on the 4th side. Find the dimensions of the field and the maximum area that can be enclosed with 1,000 feet of fence. All right, so let's draw a diagram. So you've got a river. The 4th side is a river, right? Stream, river, whatever. So there's the stream, the very straight stream. Perhaps if I put it over here. Very straight stream, so that's the stream. All right, and these animals, they can't swim, so we don't have to worry about them crossing the stream. So we don't need a fence by the stream. And then we're going to build an enclosure with 1,000 feet of fence, and we're going to build the enclosure on 3 sides, and the 4th side is the stream. All right, so we want to find the maximum area that can be enclosed. All right, so this is a rectangle. It's a rectangular field. Right, and so the opposite sides are the same. Right, so the one side is length, and the other 2 are exactly the same measure. Right, and we'll call those widths. So there's our diagram. Our primary equation is the fact that we are maximizing area, and the formula for area of a rectangle is length times width. Now we have a problem. We have too many variables, right? We can't have a length and a width. So we're going to use a secondary equation to reduce the primary equation to one variable. The a is not the problem, it's the length and the width. And you also have to consider constraints, right? Because do we have an unlimited amount of fence? If I had an unlimited amount of fence, I can make an even bigger area, right? I don't have unlimited fence. I have 1,000 feet of fence. That's all the fencing that we have. All right, so now if we look at the perimeter, our perimeter is represented by 1 length plus 2 widths. We can replace P with 1,000 because that's 1,000 feet of fence, right? The 2 lengths and the width together are 1,000. So by the way, this one is in your notes. You just don't have all the writing that I have on the side. Too bad. In retrospect, maybe the writing on the side would have been nice, but I'm going slow enough that you can keep up and add some of that. All right, so we have 1,000 feet is the length and the 2 widths. All right, so now I can rewrite this equation to get rid of one of the variables. The variable I should really get rid of is length. We should get rid of that length because it's just an L there all by itself. So if I were to subtract 2W from both sides, I'd have 1,000 minus 2W equals L, equals length. So now we can go back to that primary equation and replace the L with 1,000 minus 2W, and now we don't have 2 variables there. We only have the 1. So we have A equals, so we're going to replace this with 1,000 minus 2W, right, and then times W. So that's our new area equation. We're going to take the derivative, but you have 2 choices here. You can either use the product rule or just distribute the W and use a power rule. I'm going to distribute the W. So we have A equals 1,000 W minus 2W squared. All right, so we're going to take the derivative, and, well, I guess I already did, huh? I didn't realize I had it up there. That's okay. That was a really easy derivative to take, right? So the derivative of A is going to be dA. The derivative of and you could put dA dW with respect to W, but dA is fine, right? And the derivative of 1,000 W is going to be 1,000. Derivative of minus 2W squared would be minus 4W, right? All right, so there's the derivative. All right, now we need to look for the critical points, right? Because optimization in a lot of ways is like curve sketching. We're looking for we're looking for maxes and mins, and those are going to critical points. All right, so we're going to set this equal to 0. So we have 0 equals 1,000 minus 4W. Well, this is a pretty easy solve. I'm going to add 4W to both sides to get rid of the negative there. 4W, and I'm also going to scroll this page up. All right, so if you need to write anything down, you pause the tape. I'm going to scroll this up. If I can find the cursor, which is hiding on me. Oh, there it is. So I can scroll this up. All right, so 4W equals 1,000. Divide both sides by 4, and W is 250. All right, so that's our critical point. We're going to check that critical point by checking the second derivative. All right, and so that we're going to use a second derivative test, right, to tell us. And boy, I'm going to rewrite that a little nicer. I don't know what happened that day when I wrote this in, but that's really sloppy. So we're going to take the second derivative to verify. And this is the second derivative test. And this is the second derivative test for relative extrema. We lost a V in there. All right, so we're going to take the second derivative. So d2a is equal to, all right, so the derivative of, so here's our equation, right? Here's our first derivative. Derivative of 1,000, that's 0. Derivative of negative 4W is negative 4. All right, so we have a constant here, and it is negative. All right, so this is telling us that f of x, or whatever, the original function, let's just call it f of x, all right? So f of x, that's what I'm just going to call this so I have a name for it. F of x is concave down everywhere. And since the second derivative, f double prime of x, is less than 0, x equals negative, excuse me, our critical point, let's put critical point. The critical point, I'm writing down the derivative, the second derivative. That's not a critical point. So since f double prime of x is less than 0, our critical point is a relative maximum. Because I can't even plug it in, right? I've got a constant there, right? So that means that this is concave down everywhere. Actually, I shouldn't say everywhere. Let's get rid of the word everywhere, because this is not a function that goes on forever. There's a limit to the amount of fence we have on the domain, because there's a limit to how much fence we have. So f of x is concave down on the domain. Since f double prime of x is less than 0, the critical point is a relative maximum. All right, so we have checked to make sure. We can also use extreme value theorem to even doubly check. All right, so extreme value theorem, remember, says we test the endpoints and we test our critical point. All right, so let's use that as well. They sometimes look for this on the AP test. All right, so the I guess the smallest amount that W could be would be 0, right? That would be the smallest. I have no width at all. I just made all 1,000 feet of length. That'd be pretty silly because, well, our cow or whatever it is just going to roam because there's no width. But let's use 0, all right, as one critical point. That's, technically speaking, that's as little as the width could be. The greatest the width could be is you can make it all width, right? And since there's 2 W's, right, I guess the greatest the width could be would be 500. Also a pretty silly value. You'd have all width, no length. Right? And then we have our critical point of 250. Right? And we could check that by plugging that back into the original equation. Right? As soon as we have a width, right? So let's answer the question. And it's kind of hard to go back to the original equation to check this. So we have our endpoints, and we have a W of 250. So we'll double check this once we get our length, right? And then we can check it. Right? And so the length, which is part of this question, we'll need that to answer the full question. The length is, so I can't remember if it was to max, it was what was the area or what was the dimensions, but we'll check that when I can see the question again. But either way, I need the length. Right? So to find the length, the best equation is right there, 1,000 minus 2W. Right? So L equals 1,000 minus 2W. So 1,000 minus, let's use the 250, our critical point. And so L is going to equal 1,000 minus 500 is 500. All right. Now, if it happened to be 0 or 500, right, if we use the other critical point, if it was 0, right, the length would be 1,000. If it was 500, the length would be 0. I think we can see right away that that's not going to work out so well for us in terms of that being the maximum, right? Because if we use area equals length times width, and if the length is 1,000 and the width is 0, well, that's going to give me 0. Right? I have an area of 0. And I think these are the minimums, right? This is the minimum, not the maximum. And then if we were to use that the width was 500, that means the length is 0. So you see, those are not maximums at all. Those are minimums. You can have no area if you want. And, well, if you're going to do that, why bother to even build an enclosure? Right? But if we plug in the 500, what we got from the critical point, the area would be 500 times 250, which is, let's see, if I have 250 times 5, that'd be 1,000 plus 2 zeros, so that should be 100,000. Let me double check. Oh, sorry, I'm short 250, 125,000. 200 times 5, that would be 1,000. So 125,000 feet squared would be the maximum area enclosed, right? And so it's very clear that our critical point of 250 feet, that is the width that we would want. Now let me go back and let's double check that we answered the question, because I can no longer see what the question was. So a rectangular field bounded on 3 sides and a straight stream on the 4th side. Find the dimensions of a field with a maximum area that can be enclosed. So the dimensions are right here. So we found for fun also the area, but the dimensions would be that length is 500 feet and width is 250 feet. Now we've answered the question. Oops. And this is a popular question in Calc 1, so you should definitely be able to answer this question. Whoop, let me move that over that a little bit, see if I can get that width in there. There we go. Oops. But we're missing the line there on the T. There we go. So there's our answer. We have finished this question. I'm going to end this podcast because I think I like having one problem per video. All right, so this is a little bit shorter one. I'll see you in the next problem. Bye for now.